Hello everyone. In this video, we are going to discuss about semaphores and their use in concurrent programming. We will briefly discuss about what are semaphores, their types, how they are used and where they are used. Let's start with getting to know about what semaphores are. So basically, semaphores are just normal variables which can take an integer value and are used to coordinate the activities of multiple processes. It is a special kind of synchronization data that can be used only through specific synchronization primitives. Synchronization primitives are simple software mechanisms provided by a platform to its users for the purpose of supporting thread or process synchronization, and semaphores is one among them. Semaphores are used to provide mutual exclusion, avoid race conditions, and implement synchronization between processes. It basically has two operations, they are wait and signal. And using these two operations, a semaphore acts like a counter. Threads can wait on a semaphore to acquire a resource and signal to release it. There are basically two different types of semaphores. They are binary semaphores and counting semaphores. A binary semaphore is a semaphore whose integer value can be either 0 or 1, whereas in a counting semaphore, the value can range in an unrestricted domain. Binary semaphores are similar to a lock with two values, that is 0 and 1, where 0 means busy and 1 means free. In a counting semaphore, the value of the semaphore represents the number of processes or threads that is to be allowed inside the critical section at a time. Wait is used to get access to a resource by decrementing the value of the semaphore, and after using the resource, signal is called, which increments the value of the semaphore. As only one process can execute in its critical section at a time, binary semaphores guarantee mutual exclusion. However, in the case of counting semaphore, since multiple processes can execute in their critical section at the same time, it does not guarantee mutual exclusion. Binary semaphores do not assure bounded waiting time. However, counting semaphores assure bounded waiting time as no process will starve.
And I am going to explain semaphore operations and concurrency challenges. The two most common operations in semaphore are wait and signal. The wait is also known as P operation. When a thread or process want to access a shared resource that is protected by a semaphore, it first performs a wait operation. If the semaphore value is greater than 0, the wait operation decrements the semaphore value by 1, allowing a thread to proceed. This represents a successful acquisition of the resource. If the semaphore value is 0, then the thread is blocked until the semaphore value becomes greater than 0. The signal is also known as V operation. When a thread or process has finished using a shared resource and there is no longer in need of it, it performs a signal operation. The signal operation increments the semaphore value by 1. If there are other threads or processes waiting for the semaphore, one of them will be woken up and they will then attempt to decrement the semaphore value with the wait operation. Let's see what are the concurrency challenges. Concurrent programming involves multiple threads executing tasks simultaneously, which leads to two common issues. One is race condition and the one is deadlock. The race condition occurs when multiple threads attempt to access and modify shared resource simultaneously, resulting in unpredictable and undesirable outcomes. For example, if one thread might read data while another is in the process of updating it, leading to data corruption. And deadlock occurs when two or more threads are stuck in a state where each is waiting for a resource held by another thread, causing a standstill in program execution. To overcome this, Semaphore provides a powerful tool to address these challenges. For preventing race conditions, thread must request and acquire a semaphore so that it uses a wait operation before accessing the resource. This ensures that only one thread can access the resource at a time, eliminating the possibility of concurrent access and race conditions. For avoiding deadlocks, the semaphore manages the order of operations and allocation of resources. By carefully coordinating how thread acquires and release semaphores, we can prevent scenarios where threads are waiting for each other. So understanding these challenges and using semaphores effectively is crucial for robust concurrent programming.
In this slide, let's see the implementation of binary semaphore using this pseudocode. A semaphore is a string with two fields, q named process for processes waiting and an int value initially set to 1 for availability. The p procedure acquires the semaphore. If the value of the semaphore is 1, it locks it by setting value to 0. If not, the current process is pushed into the waiting queue and it sleeps until it can acquire the semaphore using v. The v procedure releases the semaphore if the queue is empty. If the value of the semaphore is 0, it unlocks it by setting value to 1. If there are waiting process, the front one is dequeued and awakened using wake up function, allowing it to continue execution. The system ensures controlled access to a resource. In this slide, let's see the implementation of counting semaphore with the pseudocode. A semaphore consists of two components, an integer value and a queue for process waiting to access the protected critical section. The P operation invoked with procedure P, which has an argument my semaphore, decrements the semaphore effectively, locking it if the value was initially 1. If the value becomes less than 0, it signifies waiting process, so the current process joins the queue and sleeps until it can acquire the semaphore. The V operation called with V of my semaphore, which is passed as an argument, increments the semaphore, potentially unlocking it when transitioning from 0 to 1. If the value remains non-negative, the process can continue executing. If not, first process in the queue is dequeued and awakened, allowing it access to the critical section. In this slide, let's see the application of semaphore. The first application is resource pooling. A semaphore resource pool is declared to regulate access to a shared resource. It is initially set to max resources. The acquired resource function requests a resource using the P operation, potentially waiting for 1. Afterward, it immediately invokes release resource, typically involving processing of the acquired resource. The release resource function in turn increases the resource pool semaphore using V, signifying resource availability. The loop repeating acquire resource and release resource simulate resource acquisition and release, ensuring proper resource management. In this slide, let's see the application of semaphore in producer-consumer problem. A binary semaphore mutex is initialized to 1 and it enforces the mutual exclusion, ensuring that only one process accesses the critical section at any time. Empty is a counting semaphore starting at buffer size, representing available empty slot in a shared buffer. Full is also a counting semaphore and it is initialized to 0 and it signifies an initially empty buffer. Producer and consumer collaborate using these semaphores. Producers employ P of empty function to reserve empty slot and it uses P of mutex function for mutual exclusion and V of full function to indicate filled slot after insertion, and in consumer it uses the P of full function to claim filled slots, P of mutex function for mutual exclusion and V of empty function to signal empty slots after removal. The buffer serves as a shared communication medium and the setup ensures that the safe synchronized data exchange in the concurrent systems. In this slide, let's see the difference between semaphore and mutex. In semaphore, it follows a signaling mechanism which represents the wait and signal operation. In mutex, it follows the locking mechanism. Semaphore is an integer variable, mutex is an object. In semaphore, you can get numerous programming thread. In mutex, you can get numerous thread but not concurrently. There are two types of semaphore, counting and binary semaphore. In mutex, there are no subtext included. In fact, the mutex is also known as binary semaphore. In semaphore, the value can be modified by using wait and signal operation, but in mutex the objects are locked or unlocked. In semaphore, both wait and signal operation can alter a semaphore, but in mutex the objects are altered only by the method that may release a resource. In semaphore, the value can be modified by any method releasing or getting the resource. In mutex, the object lock is discharged only by the method which has acquired the lock on it.
Slide, we'll look at how to make the most of semaphores in concurrent programming. So it is important to follow some best practices in order to get the best output from semaphores in using in concurrent programming. By following these guidelines, you can establish efficient and dependable synchronization in concurrent programming scenarios. So the first way is proper initialization. It is essential to set up semaphores correctly from the start, configuring their initial values and settings accurately. This ensures they function as intended and prevent potential issues. The next way is avoiding nested semaphore calls. Using semaphores inside other semaphore actions can lead to complexity and potential errors. It's generally best to keep semaphore operations as straightforward as possible. Then avoiding busy waiting. Busy waiting, where a program continuously checks for a condition to be met, can be inefficient and wasteful of system resources. Using semaphores to coordinate processes can help avoid this by allowing processes to wait without active checking. Then the next way is appropriate resource release. When you're done with the resource protected by a semaphore, it is essential to release it properly. Failure to release resources can lead to deadlocks and inefficiencies in a concurrent system. Proper resource release ensures that other processes can access the resource when needed. By following these best practices, you can create a more robust and reliable concurrent programming environment that minimizes issues like deadlocks, resource contention, and inefficiencies, making a software more efficient and dependable. In this slide, we look at the semaphore limitations. Semaphores are valuable tools for synchronizing concurrent processes, but they carry limitations. Misusing them can result in deadlocks where processes are stuck waiting for resources indefinitely, and starvation where some processes are unfairly delayed. Moreover, semaphores lack built-in mechanisms to address priority inversion, a problem where high priority tasks are held up by lower priority ones. Recognizing these constraints is crucial for designing reliable concurrent systems. Proper resource management and supplementary techniques like priority inheritance are necessary to avoid pitfalls and ensure efficient synchronization while working with semaphores and complex software systems. In this slide, we are going to explore some real-world examples where semaphores are used extensively. The first place where semaphores are used is operating systems. It is used in process synchronization. Operating systems use semaphores to manage the execution of multiple processes or threads. For instance, when two or more processes need to access a shared resource like a printer or a file, semaphores are employed to ensure that only one process can access it at a time, and this prevents data corruption and resource conflicts. Semaphores are used to define and manage critical sections of code. A critical section is a segment of code where only one process is allowed to execute at a time. By using semaphores, operating systems can ensure that multiple processes do not interfere with each other while accessing shared resources or variables. Semaphores facilitate inter-process communication in operating systems. They allow processes to signal and coordinate with each other, which is essential for various tasks like process synchronization, message passing, and coordination of system activities. Then it is used in database management systems. In database management systems, multiple users or applications often need to access and modify the same database concurrently. Semaphores help ensure database transactions occur in a controlled manner, preventing data corruption. For example, semaphores can be used to control access to tables or specific database records. DBMS often use buffers to cache data from the disk to memory. Semaphores are used to manage access to these buffers. They ensure that multiple queries can be processed concurrently without causing conflicts in data access or modification. Semaphores are used to implement transaction handling mechanisms, including locking and queuing. They help maintain data integrity by ensuring that multiple transactions do not interfere with each other while accessing or modifying the database records. Then, in network protocols and socket programming, semaphores are used for managing concurrent connections and data transfer. For example, a server can use semaphores to control the number of client connections it can handle concurrently, preventing overload. So, in all these real-world examples, semaphores play a critical role in achieving efficient and reliable concurrency. They help prevent race conditions, ensure synchronized access to shared resources, and facilitate effective coordination among various components, ultimately contributing to the proper functioning of complex systems. So, in conclusion, understanding and utilizing semaphores in concurrent programming provides several benefits. So, they enable control access to shared resources, prevent race conditions, avoid deadlocks, and ensure synchronization among threads. So by leveraging semaphores effectively, we can design robust, scalable, and efficient concurrent systems.